member of 40th Polish Polar Expedition to Spitsbergen on Svalbard. I'm here since July this year. I live in the Polish Polar Station Hornsund. I live here and I work here. I work here as a meteorologist, so I'm making some meteorological observations here. But as for my education, I'm a geographer with a specialization in hydrology. So we can say that I am actually a hydrologist, which is why today I would like to tell you a little bit about Arctic rivers. So let's start. Actually, I want to start with a question for you. Do you know any Arctic rivers? Any great Arctic rivers? Let's say you've got 1 minute now to think of any Arctic rivers that you might know, and I would like you to write those rivers in the chat box. The first answer is Volga. I'm not going to say anything about it yet. Okay, if not, then here you have the map of the Arctic with some, I think, the biggest Arctic rivers. Actually, I think Volga is not Arctic. But here you've got some great Arctic rivers. In the case of Northern America, that's Mackenzie and Yukon, and the rest is located in the northern Siberia. So we've got Kolyma, Lena, Yenisei, Ob, Pechoras, and Dvina. As you can see on this map, most of those rivers is actually not in the Arctic. They start far in the south, far beyond the Arctic Circle. Actually, many Arctic rivers originate in temperate and boreal forests. So why do we say that they are actually Arctic rivers? I will try to explain that to you. As a matter of fact, streams, rivers, and lakes are common in the Arctic. Why is that? Although annual precipitation, so rain and snow, is actually often very low, streams, lakes, or wetlands are particularly common and widespread due to low evaporation rates, widespread permafrost, which you can see on the map on the slide. That's the violet color. And if you don't know what is permafrost, that is the ground that has a temperature lower than 0 degrees Celsius continuously for at least 2 consecutive years. So low evaporation rates, widespread permafrost, and of course extensive meltwater from snowfields and glaciers. That's the main factors that rule the hydrology of the Arctic rivers. Furthermore, another thing is that we call them Arctic because Arctic rivers because they belong to the Arctic catchment. A catchment is an area from which surface runoff is carried away by a single drainage system, usually. But I will explain that better in a moment. As you can see on this map, we've got here catchments that belong to the Arctic catchment. They are colored in gray. So all those rivers, great Arctic rivers that I showed you at the beginning, belong to those catchments. And well, all of them and all those rivers end up in the Arctic Ocean. And if we combine this map with the map of permafrost that I showed you previously, you can see that actually most of the land in the Arctic catchment is covered with the permafrost. So that would be exactly what I told you. So let's get back for a second to the catchment. A catchment is generally a basic hydrological unit. It's a area of land which is drained by usually by a river and its tributaries. But we also can have the catchments of lakes or wetlands, for example, or oceans. And generally, each drop of precipitation, so rain or snow, that falls into the catchment area eventually ends up in a river. In one river, which is usually going to another river or to sea or to lake or a bay. And what I would like you to remember is that every inch of land on Earth forms part of a catchment. So we've got huge catchment of, for example, Atlantic Ocean. We can have some smaller catchment of, for example, Volga River. So that's the catchment. And a boundary of a catchment is called a watershed. It's a boundary line separating adjacent catchments, and usually it's a natural division line along the highest points in some area. It is, you can see that very clearly on this picture on the slide, and generally watersheds can be seen very clearly in mountain area. So that's the catchment. Okay, so let's talk a little bit about some characteristics of Arctic rivers. As I already told you, many of them originate in temperate and boreal forests. They generally vary in size, from great big Russian rivers of northern Russia to very short and small rivers for example, Svalbard or Iceland. But all of them have this in common, that they are exposed to enormous changes in the water level. That's because they usually have the dry winter, when the water level in the river is very low and the rivers generally are freezing, and there is a limited water transport. And on the other hand, in the springtime or on summertime, so during the snowmelt season, those rivers transport huge amounts of water. And together with that water, they transport a lot of sediments. So that's the main characteristics of the Arctic rivers. Of course, also what I told you before, that in the catchments you have widespread permafrost, and those regions generally get low precipitation and have low evaporation rates. And an example of a great Arctic river is, for example, River Lena. What you can see on the slide, it's a satellite photograph of Lena's delta. It is actually third largest river delta in the world, so it is quite big. But actually, all parameters of Lena River are really extraordinary. It's a really big river. If you will see the catchment area, that's over 2.5 million square kilometers. So it's far bigger than France or Germany. It's really huge area of land. Actually, that's the ninth largest catchment area in the world. So top 10 of rivers on our planet. Lena is actually also very long. It has over 4,000 kilometers long, and it starts in the Baikal Mountains, so far in the south, and ends up in the Waptive Sea, so in the Arctic Ocean. And as you can also see on the slide, it has a discharge of over 16,000 cubic meters per second, so it transports a lot of water. I will explain discharge, what does it mean, and how do we calculate that later on. If you look at this map, You can also see what I told you previously, that this is a map of permafrost in northern Russia. That whole catchment of Lena River is actually covered with it has the permafrost widespread. Okay, but are Arctic rivers really that big? Let's compare them with other great rivers that you might actually well know. Here you can see the comparison based on the amount of water that those rivers transport, so based on the discharge of those rivers. And as you can see, for example, Yenisei or Lena transport far more water than Mississippi or Ganges, which are, well, great rivers of Northern America and Central Asia. Of course, none of the great Arctic rivers transport as much water as Congo or Amazon, but still they are really big rivers in comparison to, for example, European rivers that we know, such as Danube, because Ob or Mackenzie transport more water than Danube, and far more than, for example, Rhine or Loara or Vistula. And all that fresh water is transported to the Arctic Ocean, which is also an important information. So a few words about river discharge, as I will be using this term, and I already used it. Well, in hydrology, when we talk about rivers, one of the main characteristics is river discharge. It's a volume of water passing through a cross-section of the river in a unit of time. In other words, discharge means how much water flows in a river, for example, in 1 second. We usually calculate discharge is calculated as area of a cross section of a river that you can see on the picture, multiplied by the river velocity. We usually give discharge result in liters per second or in cubic meters per second. So if you hear that a river has a discharge of 1 cubic meter per second, then you should, and you have problems with imagining how much water is that, then you can imagine 1,000 of 1 liter Coca-Cola bottles passing through a river in 1 second. And now you can imagine discharge of Lena River, which is over 16,000 cubic meters per second. That's really a lot of Coca-Cola bottles in 1 second, like millions of them. And in the literature or in many sources of information, you can also find words which are used as a synonyms of river discharge, which is generally flow, runoff, or stream flow. As a matter of hydrology, that is not necessarily correct, but I'm not going to go into details why is that. Just be aware that it can generally mean the same as river discharge. Okay, but how actually we know how much water flows in a river? How hydrologists can measure that? Those of you who have watched Winnie the Pooh may actually know one of the answers. This answer is also, in a way, hidden in this picture. If you remember when Winnie the Pooh played Pooh Sticks with his friends, that's actually one of the ways to measure how much water flows in a river. In hydrology, we officially call this method the floating method. Of course, as for hydrology, it is a little bit more complicated than Pooh Sticks, but not that much. It's a very simple and inexpensive method. And generally, floating methods, you must use some floating object. That's why the name is. And the basic idea is to measure the time that it takes a floating object to travel a specific distance downstream river. And what you have to keep in mind that this method is an indirect method. That's one thing. And what is most important, that results of this measurement are very inaccurate. You can get some really big errors, which is why we generally use this method only in case when we cannot use any other method, and only to get a rough estimate of river discharge. You can try this method by yourself if you have some small stream somewhere nearby. What you need is generally a measuring tape, a stopwatch, some boya. Personally, I can tell you that the best boya for this method, and that is recommended from most of hydrologists that I know, are oranges, because you can see them very well and they float really well in a river. And the last thing that you need is a meter stick to measure depth of a river in few places. So generally, you have to pick some straight part of a river. Let's say the length of the stretch when you will be measuring your discharge should be around 3 or 4 times greater than the river or stream width, and you just put your boya before the start of your measuring section, let's say, and you measure the time. It is good to repeat those measurements a few times and then multiply it by the area of your cross section. Another very simple and also very precise method of measuring river discharge is a volumetric method. It's a direct method which is very fast and easy, although you can only use it for very small streams. But the advantage of this method is that you get very small errors, less than 1%, and all you need is a bucket and a stopwatch. Well, it is only suitable for small streams because generally you have to find a spot in a river where it is possible to capture all the water from the stream flow. For example, at the spillway, just like on this picture. And by using a stopwatch and a bucket, you can collect the volume of water delivered by the stream during a precisely known period, because you will measure time, and then just divide your bucket volume by that time. And it's a very simple method. You can try this even at home. You can test and measure discharge of your, for example, kitchen tap. So you can try to do it by yourself and see how it goes. It's very simple. So I told you about 2 methods that we can measure river discharge. Of course, in hydrology we have many methods that we can use to measure that. They are generally divided in some groups that you can see on the slide. The biggest groups of those methods is called area velocity methods. We also have volumetric methods, hydraulic structures, and tracer dilution methods. Depending on the size of the river and its characteristic, generally we, hydrologists, choose the most appropriate methods to measure the discharge. And I can tell you that nowadays, in hydrological surveys, at least in Europe, and I think in the world too, we generally use ADCP methods that you can see on the slide. and current methods. That's because they are the fastest and I think the most accurate, so the most precise, especially the ADCP methods, because at the moment I think that's the fastest and the most precise method of measuring discharge of both small rivers and very, very big rivers, such as Lena or Amazon. And how does this look in the Arctic, hydrological measurements in the Arctic? Well, let's start with the information that hydrological data from Arctic region are sparse, and Svalbard, which I would like to concentrate on, is no exception. First, the regular monitoring station was set up in 1989 on Svalbard, and even today there are only 5 stations with continuous recording of hydrological parameters. And what I would like you to remember is that the need of reliable and accurate hydrological data is important for management of the environment and water resources. And such data are extremely scarce in Arctic regions. As for the Svalbard, what you need to know as a background for the hydrological information is that most of the land here has permafrost, and over 60% of Svalbard is covered with glaciers. Rivers here are typically short but may seasonally display very high flows, which are dominated by snowmelt and glacial melt. And this discharge is occurring mainly from June to September, so in the summertime. And except for that time, rivers are generally frozen. Well, there are some exceptions if a river is fed by the springs. But generally, rivers are frozen except for the summertime. So that's an important information. And how we actually work in the Arctic here in Hornsund, because hydrologists also work in Hornsund. Here you can see the picture from our measurements from the summertime this year. So what do we need to make actually measurements here when we go out in the field? Well, first of all, we need a survival suit. That's because if we want to get to some rivers, we have to usually use a boat, and that's a survival suit. It's necessary for the protection and just in case anything happens and if somebody would fall into the water somehow. It's also very useful because generally when you reach the shore you have to jump into the water to get off the boat. And as you can imagine, the waters here are quite cold. It is also very good because while doing the measurements you have to actually get into the river. So survival suit keeps you dry and warm. And of course, we need some measuring equipment. In our case, that's electromagnetic open channel flow meter that you can see on the picture, which is very suitable for rivers with a very turbulent flow. That is also characteristic for the Arctic rivers. And of course, we need a measuring tape to set our river profile when we will be making measurements. Yes, and you can see here another photos from our measurements that we did in the summer. Another thing that you need to make those measurements are obviously people, because you can't do those measurements by yourself here. You need to have at least 2 people to do that. But when we are going for measurements, we generally go in 3 people or even more. That is why That's because one person is generally standing in a river, as you can see on the photos, and is making the measurements. The other person is actually noting all the comments and results that the person that is in the river is saying. And another person is generally with a gun, so walking around the place where we are making measurements, looking out for a bear because, as you may know, polar bears can show up just out of nowhere. So we have to be aware of that. And also, as you can see on the photos, sometimes the velocity of those, well, in this case, very small rivers, is so strong that it's really hard to actually stand in the water. So having a survival suit is really a good thing. And as a result of those measurements that we are making, the river discharge measurements, we get a hydrograph. It's a graph showing the rate of discharge versus time in a specific point in a river. So if we have at least few results of river discharge, we can draw ourselves such a hydrograph, and which is well, as for us hydrologists, a very useful tool, and we can get a lot of information out of it. I will explain that on the example of the Gerdalen River, which is located near Longyearbyen on Svalbard. As you can see, this graph starts in May and ends in December. That's because flow of water in Arctic river has generally seasonal character. So we have a very low discharge during the dry and cold winter when usually rivers are freezing here. That's why this graph starts in May, because simply from January to May there was absolutely no discharge, no water flow. And you can see that after May we have a very rapid increase in discharge. That's because all the ice and snow is starting to melt. So we have a very high discharge during this normal season. And then we have the gradual decrease in the discharge as the amount of snow and ice is decreasing, and there is not that much of water that can melt. And sometimes there is a small increase after some rainfall periods. So that's the characteristic of the flow. Okay, and now I have another question for you, because I talked a little bit about this discharge, river discharge. How do you think, do we actually need that kind of data in our everyday life? And if we need, then maybe you have some ideas where we could use the river discharge data. What for? Is it important? How do you think? I see some silence in the chat box. Or you have actually no idea how we can use it, then I will help you with that. Hydroelectricity, yes, definitely. That's a good hint. Well, generally, river discharge data is actually essential for many important uses. River discharge data, or in general hydrometric information, is actually fundamental to the planning, operation, and management of water resources and flood defense. So that's the first thing. Why is that? Well, river discharge is a combined result of many climatological and geographical factors which interact within a catchment. This integration implies that river discharge is actually the most directly appropriate component in the hydrological cycle for a wide range of applications. And these include, for example, assessment and management of water resources, design of water-related structures, and, for example, flood warning, and also this discharge data is actually essential for assessing and developing hydropower potential. So actually, yes, hydroelectricity. Also, it is very useful for determining water quality. And believe me, that's only some of the most important things that we can use that kind of data. So it is really important to measure how much water flows in a river. And also another thing connected with rivers that I would like to tell you, that's floods. Are there any floods in the Arctic? Yes, there are. The largest floods, as you can probably imagine, we have in the late summer, which is caused by heavy rainstorms and glacier melting. And that kind of flood can completely reform river channels that you can see on this photograph on the slide. And also they transport huge amounts of sediment, which is also visible on this photo. Sometimes we have floods connected to ice breakup, which can pile up and jam the flow. And in this case, also huge areas can be flooded. And also during the floods, we have very big riverbank erosion, and sometimes even infrastructure can be damaged because, for example, bridges might collapse if this is a really strong flow during the flood. And I would like to finish this lesson with a statement that I would like you to remember, that Arctic rivers are important. Why? Well, thanks to hydrological surveys around the world, we know approximately how much water is flowing in the Arctic rivers and all rivers all around the world. And changes in river discharge also impact coastal and ocean chemistry, biology, and circulation. That's the key word here. This interaction is particularly strong in the Arctic because rivers in this region, so those great Arctic rivers that I showed you at the beginning of our lesson, transport over 10% of global river discharge. But the Arctic Ocean contains only 1% of the global ocean volume. So it's all about the proportions here. And reduced salinity and density have been observed in the North Atlantic Ocean, as melting ice and increasing river runoff have added more fresh water to the ocean. And if this trend persists, it could cause changes in the ocean circulation patterns that strongly affect regional climate in many places that are far from the Arctic. And actually, you can learn more about this on the lesson that is called "What Happens in the Arctic Doesn't Stay in the Arctic." So I encourage you to join to that lesson. And with that, I would like to thank you for your attention. You have listened to me for quite some time. And now your turn. Maybe you have some questions that you would like to ask me.